All right, so in the last video, we covered free particle movement in one dimension. And so for this video, what I'll be talking about is restricted particle movement between two walls. But to first set up the equations for today, I need to talk about the probability density and how we can get that. And so I told you last time that psi is a wave function, right? Well, I was already showing you that there's imaginary sometimes values when I was talking about the momentum operator when there was an h bar over I. And so you can imagine that there is complex wave functions, and so there's obviously going to be the complex conjugate of that. And so how we label it is psi is going to be the wave function, and psi star is the complex conjugate. And so sometimes the wave function is completely real, in which case psi star is also included, but psi star ends up just being psi. And so what we need to know is the probability density of finding a particular particle in a certain position is given by psi star times psi. And so if we multiply these two wave functions together, we end up getting a curve. You can think of it, let me draw an example. So we would get a curve maybe, oh, that's a horrible curve. Let me draw that axis better. We can get something like this. You might think of it as sort of like a bell curve sometimes. And so this would be what we were plotting with psi star and psi multiplied together. And then you can, take the area underneath it and predict where is the particle most likely to be. So it would be most likely to be here, right? But the way how we get this curve is through psi star times psi. And something in statistics that you should know is when we have a curve like this, it's always important to normalize it. What does normalizing mean? It means that this area has to equal 1. So that allows us to make our probabilities as a decimal or percentage. And so you'll see that when we integrate this, it's important to get it to 1, and for that degree, we will need a normalization constant sometimes to multiply the wave function by. Okay, so now that we've set up what a probability density is, how we calculate it, and normalization, we can continue on to restricted particle movement between two walls. So let's write that down. So let's say that we have, a particle trying to be within one wall at x equals 0 and x equals L. And so inside, between these two walls, we'll assume that these walls are perfectly rigid, by the way, that no particle can get through. And so what that means is in this area, it is very similar to the free particle in one dimension. There's no forces acting on it, so our potential, we can set it as 0. But outside of when we go to this direction or this direction, outside these walls, the potential is actually infinity. And the reason for that is when we set the potential to infinity, if you look at Schrodinger's equation, right? I'm anyways going to write it out. So we'll label it as, if we look at the Hamiltonian, we have this, right? We have the kinetic energy portion, and then we tack on a potential portion. So if we think about this, right, and this is infinity, this whole thing is infinity, the only way how we can solve h psi equals e psi, the only way how we can solve this equation is if psi ends up being 0. This is assuming that the potential is infinity. And so that means what that implies is that if you remember that probability density is psi squared, that means that if we square 0, we get 0. And so we have 0% probability of finding the particle out here or out here. And that's what we want because we're assuming that these walls are completely rigid. And so that's why we have infinity, the potential has infinity on both sides, but 0 in the middle. And so once again, we can think back to how we found psi in the previous example. So we still have the same oscillatory functions. So we have possible psi's as we have a sine kx, we have a cosine kx, and we have a e to the plus or minus ikx. All right. But now we need to decide on which one of them is best. So one thing that we need to keep in mind is that now we have a boundary condition. And what is that boundary condition? The boundary condition is basically saying that at x equals 0, the potential is 0. And on the other side, it's also 0. And what this means is that we won't find the particle on that wall, basically, because it's a perfectly rigid wall. We can't have it on this. It has to be in between, not on it or beyond. And so if we apply these boundary conditions, what we can see is if we say psi of 0, right? Let's plug in 0 for each of these equations. If I plug in 0 for x here, I get e to the 0, which is 1, times a, which turns out to be a. And the same thing is of cosine of 0. Cosine of 0 is 1, and so we get a. But in sine, we see something different. So if I plug in sine of 0, I get 0. And so 0 times a is 0. And so you can already see that we have a winner because a sine kx is the only one that actually satisfies one of our boundary conditions. It's the only one that satisfies the fact that psi of 0 is having to be 0. And so we already have a winner here. So I can take a check mark here. And these ones are not valid. Okay. So then we can continue on with the second boundary condition that psi at L equals 0. And so what I can write is psi of L equals a sine KL. And that equals 0. Okay, so we divide both sides by a, we still get 0. And then if we solve for what KL is, we know that sine is only equivalent to 0. If you remember your unit circle, sine is only equivalent to 0 at n pi. So we know that KL equals n pi. Sine is always 0 at n pi. And so solving for k, we get, or actually we want to solve for L. So let's solve for L. L is equal to n pi over k. Okay. And so writing what psi is now, we can write psi n of x is equivalent to a sine n pi x over L. So this is our new psi. But there's still something missing, right? We don't know what this a is. And so that's where normalization comes into context here. And so what does it mean to normalize? To normalize for the probability density, this means that 1 is the area under the curve. And so how do we define mathematically what the area under the curve is? It's through an integral. So I'll write an integral. And so we're integrating from 0 to L. And it's going to be psi star psi dx. But psi star, as I said before, if psi is real, there's no imaginary portion. This just ends up being equivalent to psi squared. And so if you go through the math and actually solve for what A is, you'll figure out that A is equivalent to 2 over L square rooted. And so that will give us our total psi function. So psi of n is equivalent to 2 over L to the 1/2 times sine n pi x over L. Okay, so we figured out what our normalization constant was. We figured out what psi is, but again, like last time, our main goal was to figure out what E is. So how do we figure out what E is? Well, let's plug this psi in, right? Let's plug it into the Schrodinger's equation. So if we plug it into minus h bar squared over 2m del squared over del x squared psi of x, I'm not going to write it all out. What we end up getting is that E sub n is equivalent to n squared h bar squared, all of that over 8m L squared. So you can go through the math and this will check out. And that's how we get what E is. But you can see now we're relying on a different variable. So energy is dependent on n. So if we were to graph this out graphically, what this would look like is at n equals 1, we have 0, L, and if this is x, what we would see is this is psi of 1, we would see it looks like this. And then for n equals 2, it would look something like this. And we can continue on. I'll go up to n equals 3. And so we'll see something like this. Little cramp there. But yeah, so this is what all the psi's are. And then if we want to look at the probability density, remember this is nothing but the wave function squared, since this is all real. It would look something like this. This one would look like this. Oh, that's a horrible drawing. But you can imagine that, you know, this curve is the same as this, and as it gets squared, it just gets flipped up. And then this one is three peaks. And so this is what they look like graphically. And so in this case, now we have an n, and I'm going to let you know that this is the start of our quantum numbers. So we have now quantum numbers, n as the first quantum number. And we'll be seeing in the next videos as we go through transmission through barrier tunneling, we'll introduce a new quantum number. And these quantum numbers are really important because they'll allow us to, you know, specify different parameters for atoms and such. But it's important to take note of where these quantum numbers are appearing from. And so this is our first one. And so in the next video, I'll be going over tunneling. How a particle, because in this case, we had the particle not being able to move through these walls, but particles can tunnel since this is quantum mechanics. We're not in classical physics anymore. So we'll be talking about that in the next video.